Second part of 8.2, equilibrium of rigid body. So in this video, we're going to solve a problem related to equilibrium of a uniform rigid body. Okay, so the conditions for static equilibrium of rigid body, you need to remember of two things. The first one is summation F equals to 0, meaning that the rigid body is not moving along X or along Y. And then the sum of all torques about any point on the body is 0. So summation of torque at any point on the rigid body is equals to 0. So for this diagram, the rigid body is the ladder that we put at rest against a wall. Some of the problems that you might need to solve for this kind of question are to find the reaction at A, reaction at B, and also to find the coefficient of friction force. So for that, the first thing you need to do is to draw a free body diagram showing and labeling all external forces acting on the body, and then resolving the forces into X and Y components. So this one will involve resolution of vectors. Then apply the first condition, Fx equals to 0, Fy is equals to 0. Next, take torque about any convenient point in the system and equate the sum of the torque to 0. Okay, so the reason why we equate the sum to 0 because there is no rotation for the rigid body. So the rigid body is in static equilibrium, which means that it is not moving on X or Y axis and also not rotating. So from the equations that we can get from Fx, Fy, and also torque, we can solve the unknown quantities. So here is some useful tips to solve problems related to equilibrium of a uniform rigid body. The first step is to choose a point with two or more unknown forces, because this will help to simplify the torque equation because the torques produced by these forces will equals to 0. Pilih tempat yang ada banyak force untuk mengurangkan calculation torque. So, jadi equation torque akan jadi lebih pendek. Then, weight of object is acting at its center of gravity. For uniform object, weight always acting at the center of the object. Okay, so when you are given the mass, you have to calculate the weight and then label the weight vector on the FBD. Dia mesti berada di tengah-tengah. Next, the word rough and smooth have a particular meaning in physics. So kalau rough, meaning that you need to consider the friction force. Smooth, treat it as friction free, tak ada friction. Okay, let's look at example 1. A ladder against the wall. A uniform ladder of mass 30 kg. So given this is the mass of the ladder, this ladder is rest against a smooth wall. Okay, so the keyword here is smooth wall, and then its lower end on rough ground. Okay, so the first statement gives us the idea that we need to consider the weight, and this ladder is a uniform rigid body. So to draw the vector for the weight, it must be located at the center of the ladder. Here is the center of the ladder. So this length over here is half. It becomes 1.5 meter. Then rest against smooth wall, meaning that at point A, no friction. And then its lower end on rough floor. Therefore, at point B, there will be friction force. Calculate the reaction force at A and B. So cari force yang bertindak pada point A and also force yang bertindak pada point B. Then calculate the coefficient of friction between the ground and the ladder. So to get the coefficient of friction, you need to calculate the magnitude of friction first. Okay, the first step is to draw the FBD. Okay, at point A, the ladder is touching the wall. So when there are two objects in contact, there will be normal force or reaction force. Okay, so now the surface is the wall. The wall is vertical. Therefore, the normal force will come out from the wall, 90 degrees to the wall, going to the left. Okay, so make sure that the directions of NA is correct. Okay, takut ada yang pergi lukis ke atas. So here we have NA. And then given that we have a weight to consider, so this is NB. So also mentioned in the question that at B, this is a rough floor, meaning that there's going to be a friction force. But then what is the directions of the friction? Okay, remember, friction force always oppose motion. Okay, and then this ladder will have the tendency to move to the left. Okay, so the friction force must oppose the motion. So friction force going to the right. So we can draw the vector of F. In total, we have 1, 2, 3, and 4 forces for this rigid body. Okay, and then we remember that the condition for a rigid body to be in equilibrium is that summation of Fx equals to 0, Fy equals to 0, and torque equals to 0. Okay, for the x component, we have friction force and Na along x-axis. So we can write the equation. The right is positive, to the left is negative. So F minus Na is equals to 0. From here, we know that the magnitude of F and Na are the same. But then we are not able to solve this equation yet because lack of information. Tak cukup maklumat lagi. Okay, next we go to Fy. Fy, we need to consider all forces along Y. We have NB and W. Going up positive, going down negative. So NB minus W is equals to 0. NB equals to mg. Okay, so we can find the value for NB. The mass is 30 kg times 9.81. The answer is 294.3 Newton. Okay, the next condition is summation of torque equals to 0, meaning that the rigid body is not rotating at any point. So you can say the summation of torque at B equals to 0, summation of torque in the middle equals to 0, the summation of torque at A is equals to 0 at any point because all particles along the rigid body is not moving. Okay, so based on the tips that we have seen earlier, choose a point that consists of two or more unknown forces in order to simplify the torque equation. Pilih point yang ada banyak forces supaya equation torque kita lebih pendek untuk diselesaikan. So from our FVD, the point that has two or more unknown forces is point B. So this one will be the point of rotation. Kalau kita buat di sini point of rotation, torque untuk NB dengan F dah equal to 0. Okay, sebab apa? Sebab kalau kita kira torque for NB is equals to NB times with the D. Tapi D equals to 0 because the forces is exactly at the point of rotation. So this one becomes 0. The same for friction. The torque for friction is equals to friction times D. D is 0. So no torque produced by NB and friction force at point B. Okay, so our equation will only consist of torque from NA and W. And let's say if we choose A as the point of rotation. So torque due to NA will become 0, but then we have three forces that we need to consider in our equation for the torque. So this one will be a longer equation. So that's why that we choose point B as the point of rotation. Okay, so let's calculate the torque due to weight. So this is the line of actions of the weight. From the line of action, 90 degree directly to the point of rotation. So this is 90 degree. This is D1, the moment arm for the weight W. Okay, so the directions of rotation. So this is the D, horizontal. Weight is going down. So the rotation would be clockwise. So for clockwise, the sign convention is negative. So W will give negative torque. Okay, next for NA. So this is the line of action for NA. 90 degree from the line of action straight to the point of rotation, 90 degree. So this is D2, the moment arm for NA. So the directions of rotation for NA. So this is the D, D2, and this is the directions of NA. Therefore, the directions of the torque would be anti-clockwise, and anti-clockwise is positive torque. NA will give positive torque. Okay, so we can expand the equation. Summation of torque is equal to 0, which is due to torque NA positive minus torque W equals to 0. Torque NA is NA times D2 minus torque W is W times D1 equals to 0. So next we have to find the magnitude of D2 and D1. This one will involve trigonometry. So for D1 will consider this triangle over here. Okay, so the angle is given in the diagram. Okay, and then the original length of the ladder is 3 meter. So half of it is 1.5. Therefore, D1 is equals to 1.5 cos 50. Then for D2 will consider this triangle. Okay, so the triangle for D2 could be like this or like this. Okay, it's up to you. Either way will give you the same answer. Okay, so for me, I would like to do D2 is equals to 3 sine 50. So if you notice, the length of the rigid body for this triangle is 1.5, but then for this triangle, the length of the rigid body is 3 meter. So next, we can substitute the value. We don't know what is NA, but D2 is 2.2981 minus W. Okay, W we have calculated. Okay, this one, which is 294.3. And then D1, 0.96418. Okay, so then we will get an A 123.48 Newton. Okay, let's say if you didn't change this to decimal point, you can directly insert 1.5 cos 50, you might get 123.45. Okay, so perbezaan yang sangat sedikit lah. Okay, so we need to find NB, dah dapat. NA, okay, kita dah dapat nilai NA. Soalan minta mu. Okay, so from there we know that friction force is equals to mu N. Okay, equals to NA. NA 123.48 Newton. Okay, so in the diagram, friction berlaku pada point B, therefore mu NB. Mu NB, so we can calculate mu 123.48. This is NB. Okay, so the mu, the coefficient of friction is 0.42. And there is no unit for mu. So we've got the answer for coefficient, the mu, and then also for A. Then for B, we have not settled yet. Okay, because at point B, we have normal force going up, and then we have friction force. So the reaction, the total reaction, is the resultant of the two. Okay, so this is resultant B. Reaction at B, RB is equals to, using the formula for magnitude, so NB squared plus F squared. Then you will get the answer. 319 Newton. Okay, the next example is for cable and rod. So given a uniform beam is supported by a wire making an angle of 37 degrees. So this is the angle of the string of the wire and hinge at wall. So this beam is attached at the wall at point B. The beam has a weight of 150 Newton and this is a uniform rigid body. Find the tension and the horizontal and vertical component of the exerted by the hinge on the beam. Okay, let's first draw the FBD. So the rigid body is the beam over here. There is a tension from the wire. And then this beam has a weight going down. And then for the hinge acts as a support. So kalau untuk support, the hinge prevent the beam from moving along Y and X axis. Okay, so there is actually a reaction force along X and reaction force along Y, preventing the beam from moving. Okay, dan kita tak tahu arah BX dengan BY ni arah mana. Kita letak saja, pilih saja satu direction. And then from the calculation, kalau kita dapat negative, meaning that the reaction force, the opposite of what we have drawn in the FBD. Okay, and then for A kita tak label apa-apa because we are focusing on the rigid body. Okay, rigid body ni dia touching tak point A? Tak. Yang touching point A adalah wire. Tapi wire ni dia touch, dia contact with the beam. Jadi kita lukis FBD untuk beam sahaja. Okay, untuk reaction dekat B, kita boleh namakan apa-apalah. So, saya nak namakan based on the point. So, this is BX and BY. Okay, so this beam is in static equilibrium. So summation of torque equals to 0, summation of F equals to 0. So the point of rotation that will help us to do our calculation should be point B lah. Sebab point B ni dia banyak force. Kalau kita letakkan point of rotation dekat sini, kita tidak perlu kira torque due to Bx and due to By. Jadi equation kita akan lebih mudah. Okay, so let's say this is the point of rotation. From the point of rotation to W, 90 degree to the line of action, this is D1. Okay, moment arm untuk W adalah D1. Okay, next, from the point of rotation, straight pergi dekat T. Okay, so to calculate torque, kita akan pakai F darab dengan D. And F and D should be 90 degree. So, kalaulah kita punya D horizontal, kita punya T mestilah kita ambil 90 degree dengan dia. Okay, so the next thing is kita kena resolve. This one would be Ty and here would be Tx. Okay, so therefore component Y for T yang akan menyebabkan torque. Okay, sebab apa? This is D2. Okay, D2 the blue color and then we have Ty. So this one will rotate anti-clockwise. Okay, how about Tx? Okay, so this is D and then this is our Tx. So the angle is 180 degree. Sin 180 is equals to 0. So Tx will not contribute to the torque. Okay, dia akan jadi kosong lah. Okay, therefore untuk T kita hanya ambil kira Ty. Okay, so torque due to Ty, this is the D, torque going up. So the direction is anti-clockwise. This one you will get positive torque. Okay, for the W, this is the D, W is going down. So the directions of rotation is clockwise. Clockwise is negative. Okay, so we can start our calculation. Summation of torque is equals to 0. And now we choose point B. So the torque about point B is equals to 0. Okay, so then we have torque due to Ty positive minus with the torque due to the weight equals to 0. So torque Ty times with D2 minus W times D1 equals to 0. Okay, and then the weight of the beam is 150 Newton. And then Ty is T sine 37. Okay, substitute and expand the equation. Then we will get T sine 37 L equals to 150 L. Then we can cancel L on both sides. Okay, then we will get the value for T, which is 124.6 Newton. So we've got the tension. Next, we have to find the horizontal and vertical component by the hinge. So we need to find By and Bx. Okay, the summation of Fx equals to 0. So the forces acting along x, we have Bx minus Tx equals to 0. So Bx is equals to Tx. Tx is T cos 37. Substitute T cos 37. And then we will get Bx equals to 99.53 Newton. Okay, then the summation of Fy equals to 0. So all the forces along y, we have By going up positive plus Ty going up minus W equals to 0. Okay, so we need to find By. By is equals to W minus Ty equals to 150 minus Ty. So Ty is 124.6 sine 37, 74.986. So By is equals to 75.01 Newton. Okay, so we've got all the answers.